Hello everyone, I'm back again and here's the question. How much of you know what is the volume of a sphere? And if you know this, how much of you know how to derive it? I mean, how can we possibly understand the volume of a sphere is 4 by 3 pi r cube? And if you are able to derive it, now I will ask you, can you derive it without calculus? And if we are using calculus, can you define each and every step of that calculus? Here I am talking about digging deep into the rabbit hole to the fundamentals of mathematics and finding the simplest possible shape in universe and its volume. We all use it, we see it every day. But how did we calculate it? And if you are using calculus, then you are doing it totally wrong. You are running away from the main curiosity or the main ingredient of the mathematics. You are just using the result which Newton or Leibniz derived. But the volume of sphere was first or as we know by Archimedes. Here what I will do today, I will not use any bit of calculus and derive the volume of sphere 4 by 3 pi r cube from the smallest possible axioms we can have, or I can say when Euclid elements, that we use that simple axioms, and it's little bit confusing or sometimes paradoxical topic of infinitely small. So let's get started. Before going to three-dimension shapes, first let's see, and I believe most of you must be knowing the area of the circle is pi r square, where pi is the ratio of perimeter to the radius of a circle. So how do we come up with this area? This is also I'm expecting most of you must know, and if you don't know, here is a very beautiful and very small proof if we compare to the other massive proof coming ahead. What I am asking you to divide this circle in triangles, just like pizza makers do. But because we are not making pizza, we can go infinite precisely small and small and small. You have to divide this circle in infinitely small pieces. And once you are done these pieces, now I want you to arrange them. Take pieces in pairs here and arrange them like this. Now take another pair and arrange them again like this. When you are done arranging all of the pieces, this is, I make a mess of the drawing, but I think you get the point. When you arrange all of these triangles in this rectangular shape, what you notice, this outside shape, outside of both of the sides is just the perimeter, and whole of the perimeter is covered here. You can see actually it's a parallelogram, but it's approaching towards a perfectly rectangular as we chop even smaller and smaller and smaller pieces. And we know the area of rectangular, its length times breadth. Its length is just the perimeter, but used to be 2 pi r. Actually, its length is half of that, because half of our perimeter is on upper section and half on the other section. So we divide it by 2, and its breadth, or you can say the width of this rectangular is just or it's approaching the radius of our original circle. And if you multiply with our r with little bit simplification, we get pi r square. So that was pretty neat proof. And now, if you know this much, you know enough about the basics, and you are eligible to see the proof ahead. It will go beyond this simple logic, but their speed remains the same. We want to understand the basics. We want to understand the formulas which our teachers used to force us to learn, to cram, and now we want to derive that from their fundamentals. No question asked. And we want to make the beauty of the mathematics, of the proof, of the rigorous proofing, and on the smallest or simplest possible shape, which is sphere. So how we approach to that? So I have here the steps. First, we will go and see how to calculate volume of other shapes, and if we will see if we can relate them to sphere, because sphere is very complex and curvy shape. We cannot approach that shape directly. Circle was easy, we were smart, but sphere is not that much easy. So let's tackle some simple problem, and we will modify those problems, tweaking into that problems, and move towards the higher shape and ultimately to the sphere. So the simplest possible 3D shape of which volume we can calculate is the pyramid. Egyptians made pyramid, and I'm pretty sure that they knew some of these calculations, because they need to find how much material they were going to use on that pyramid. And you will see it's very easy proof if we talk about pyramid. For this proof, I want to use your imagination. I want you to imagine a dice, a perfect cube. We say that cube, a perfect cube. Let me draw it for you here. Don't rely on this drawing. We need very strong imagination for what is coming ahead. This is just a little help giving us. Now what I want you to do is take its center and draw lines to all of the 8 edges. I'm not drawing all, I'm drawing just one, because I want to show you that I got a pyramid here, and base of this pyramid is the one face of the cube, and its height is just the center of our cube. So how much of these cube pyramids can we make? Due to the symmetry of shape, we have 6 faces, so we get 6 pyramids. And due to the symmetry, here is the very crucial one, they all have same volume. So what was the volume of our cube? Cube volume is just, if this side was A, the cube volume is just A cube. That's a simple, very simple shape. So what is the volume of this pyramid with dimensions where height is half of the base of this square pyramid? It's just A cube by 6, because all 6 pyramid got the same volume. Now you should ask me, but this calculation is true for very specific type of pyramid. It should not work on all of the pyramid. And yes, you are right, because we have just taken a very specific kind of pyramid where the base is a square and its height is exactly half of the side of our base of the pyramid. And still it's not looking very well. So let me make some tweaks here, and we will move toward generality. we will generalize some result. Now I want you to chop this other half of the cube away. Just get rid of them, because we are only interested in our one pyramid. So here what it looks, we have a box and it's perfectly enclosing this pyramid. So listen to this statement carefully. If I have a box and I make a pyramid in this, for now, let's say, given the specific dimensions of half the height of the base, I can say that pyramid covers 1/3 of the area of the box. This is a very big statement, and still we are not general. I will move toward generality here, but I want to make you a quick analogy between what we used to do in two dimensions. We used to find the area of a triangle just by half into base into height. Here we are getting 1/3 of the area of the box. And what was the area of the square here, in the square in which we are enclosing? Let's say if we are not using any obtuse triangular, then it was just the half of the area. Sorry, we have to use the volume because it's in 3 dimension. But in 2 dimension, what we was having, half of the area. Any triangle, no matter what was its size, it will cover half of the box which it was rectangle in which it was enclosed. And in 3D we are getting, with certain circumstances, 1/3 of the volume of the box. But what if this specific result can be converted into journal? Then that would be a very bingo moment for us. And this is exactly what we are going to do, because we know in 2D this is a general case, in 3D it should be general case, and we will prove that it is the general case. That you give me any 3D box and I will make any pyramid in that, and that volume enclosed by that pyramid would be 1/3 of the original box. So let's move towards generality. So here is our box. We have pyramid in it. Now what I will do is, I will take this same box, I will hold it from one end and other from other hand to the lower end. I will stretch it. Think it's mathematically. I am stretching it evenly. I stretch this half of the cube to make a very long cuboid. Now what happened when I stretch this? This pyramid also stretch with this, and now I am getting a unusual shaped pyramid. Now we need to understand mathematically what does stretch mean. Stretch, squeeze, shear, these words are very intuitive to understand, but what does they mean mathematically? Here I will start with 2D analogy and then move towards 3D. If I have some random shape, two random shapes, one get area A1, second got area B1, and now imagine they are on a rubber sheet, and I started to stretch this sheet so it become elongated. Now before elongation, its a ratio of its areas were a dash by b dash. What would be this ratio after I stretched? And if you are guessing a dash by b dash, you are exactly correct. But why? Why does this a does not affect by that? Because even if we are stretching on one axis, not on both of the axes. For that you can think now, like we imagine infinitely small triangles there. We imagine infinitely small grids make on them. Now if you think of a square in this grid, and if I stretch it, it just become a rectangle. And the big thing is, all of the square becomes a rectangle by the same factor, and the change in area from this square to rectangle remains fixed in all of the shapes. So does this ratio becomes same. And that's very simple analogy can be worked in 3D. This time instead of squares we are using cubes. And after stretching, when I stretched this box, our cube turned to a rectangle. And we can make infinitely small squares or rectangles here. And if this ratio was true in 2 dimension, in 3 dimension, but I can say no matter height of the box, no matter width of the box, no matter depth of the box, the pyramid will occupy exactly 1/3 of the volume of the box it is enclosing. And this result is remarkable one. The day I knew it, I knew that today my day has become successful. And I hope if you learn this now, your day is successful. And this is what made Archimedes one of the biggest mathematicians. This small simplification is so brilliant, so powerful. Now that we will see from this simple remarkable result, we can go on and find the volume of sphere. The statement is simple. You give me a box, I can find the area volume of the pyramid enclosed by this. Next, now let's move to level 2. We are done with pyramids. So we are done with pyramids, and we'll move towards more general result. We'll keep on generalizing till we reach the sphere. Now I want you to think is, instead of stretching, we will use shear. What does shear mean? That I am holding the bottom of this cube and pushing the this side up from upside to make this shape a parallelepiped. If I'm pronouncing it correct, but you will get a shape something like this. This is called shear. And what if that ratio result of the any square or rectangle in this true for shear force also? And we have already proved it's true for stretching, squaring along any direction. We will not use that lose that ratio between the two shapes in our entire volume. And again, I will go to 2D to understand, to make things clear, and then jump to 3D. What we have in 3D is, when we have a rectangular and we shear it and make a parallelogram, you don't need very high mathematics, or you can use even 8 to 9 standard books to see that both have same area. And in 3D, this parallelepiped or whatever you can name it is just the result of this effect in 2 dimension separately. And so if I stretch it in one axis, its volume is not changing. Think about this. And if I stretch it in another direction, still its volume is not changing, because these are just the same parallelogram shifting. Its height will be same, base into height. Its height will be same, base into height. And if I make shear on our original pyramid, now I am getting a weird shaped pyramid. But the $1 million talk is this, that volume of this pyramid is still 1/3 of its base area into height, which is 1/3 into base area into its height. And we have done this proof from the bottom, the deepest part of the mathematics. We built on the logic, and we came up with this beautiful result. And it is remarkable. It's just remarkable if you ask me. Now, if you accept this theorem that a 3D equivalent of area of triangle, which was half into base into height, it was the general formula for the area of triangular. In 3D, a 3D counterpart of triangle, any shape, its volume would be 1/3 base area into its height. And we have not rigorously but kind of prove this result. You can move more into rigor, or I will share my paperwork, but that rigor would be too much long for a video, especially on YouTube. So, accepting this result, I can say that if I take a cylinder, place a cube in it, the volume of the cube would be 1/3 of the volume of the entire cylinder. And we are using just the same result which we have proved in last 20 to 25 minutes. And we proved this result from the basic, the depth of the mathematics. We proved this, and now we are using the same result to make a new conclusion, that the volume of the cube of cone is 1/3 of the volume of the what we say, cylinder it's enclosed. All of this was done to come to one single conclusion. And first time in this video we will talk about sphere, and we are very close now. We are very close to making that remarkable result, how to find the volume of the sphere. Now, for the first time, I am drawing here a sphere. Think of this in 3D. It has a radius of r. Now we need to think little bit more 3D, so try to resonate with me here. I'm taking a disc on this cylinder, on this sphere, at some arbitrary height from the center, and center of this is at h height from the center, and the radius of that disc I'm using is, say, b. And just to make things little bit more complicated, but it will help later, take its width dh. And imagine this width is infinitely small. We are just taking it for a sake of width, just like a plane. There is no difference between h from its upper portion to lower portion. But because we are finding volume, we need some three-dimensional element. That's why we are taking it small width. Now, if you know Pythagoras theorem, which we have made videos also on this channel and almost on every channel related to math on YouTube, you'll find a video about Pythagoras theorem. We will use that theorem here. Here I got a right angle triangle, and what relation this right angle triangle gives me is r square is equal to b square plus h square. With a little bit of reshuffling, b square is equal to r square minus h square. Now, what step I am going to use is, I do not expect anyone to come with that in their mind. Even I also was not able to come this by my own. I get help from the book called Measurement by Paul Lockhart. I definitely recommend you that book. So this final step is the smartest of all the steps, which we can guess Archimedes was the first person to come up with 2000 years ago, and even 1500 years before the calculus was invented. So what he used is, he used analogies. Analogy is a thing which we humans have perfected. It's perfected by our evolution. It's helped us in forest, but now it is helping in our math, physics, chemistry, engineering. So what analogy he did? He used. He already know the volume of a cone, which we have derived in this just a couple of minutes before. He look at these both shapes and try to make some similarities, or specifically this equation. One more thing I want to clear you, that at that time Archimedes, they didn't have these luxury of using symbols of squares. They have to do most of the things intuitively. They didn't develop a very good number system or algebra system. So for Archimedes it was even harder, because we can use this arithmetic. At that time it was not so simple. So just saying, we'll use this algebra anyway. So Archimedes said, what can he see similarity in both of them? Or can he find this equation here? He did one thing. He take this width to be same as a sphere. From center at every point, this width is going to be r square. And the point where this our cone finishes, he used it as h square, where we are using h as a height in our this figure. Now thing seems might confusing to you in this diagram, so I'm tilting this one diagram, this diagram, so things get even more clearer. So we have our cone, in fact a little bit longer because its radius is same as the original sphere. This is our height r, which is fixed here also, which is fixed, and I got h square. Now the question is, what is the volume of the cylinder other than cone? Or simply, if I take out the cone, how much juice is left in this cylinder? And equation of that would be r square minus h square, at least for some section, for this section or this section on both sides. So it's a 3D figure, don't forget. And just like we use in circle analogy, we take that small infinitely PC and started stacking them to get the original volume. We will do the same here. I will take this infinitely small pieces of dh and start stacking them. If I start stacking them, all of these pieces, what I get? A hemisphere. What if I start stacking all of these pieces here, of which are governed by the same equation? I will get a cylinder with a cone cut out from it. Our main aim was to find the volume of this hemisphere or the sphere, but we find an analogy, we find a other shape using governing the same equation, having the same volume, and now we can find its volume. Its volume is just volume of cylinder minus the volume of cube. What was the volume of cube here, of cylinder here, which is just as it was r height pi r square into r. It was pi r cube. And now we are removing one third of juice from it and taking 2/3. We multiply it by 2/3. So 2/3 pi r cube is the volume of hemisphere, and now you must know the final answer. We stack two hemispheres to make a sphere, and the volume of the sphere becomes 4/3 pi r cube. So if you are till here in this video, that means a lot to you also, maybe to us also, and if you learn something from here, very good. See you later. Keep curious and stay informative. Over and out.